Bismillah ar-Rahman ar-Rahim. Assalamu alaikum everyone. Today we're going to learn 16.2. It's called electric force. 16.2 is the largest and most important lesson in chapter 16. In fact, we're actually going to split this into two separate sections just to make it a little bit more manageable. So you guys are coming fresh off of a relatively simple lesson that, reminded you of things like positive charges and negative charges. Um, and that's essentially all that was going on in those situations. Now, today, just to motivate you to think about this a little bit, today what's going to happen is you're going to be working with uh, two different types of charges. You'll have a positive charge and you'll have a negative charge, right? And we're going to learn that everybody knows that there's a force between a positive charge and a negative charge, but what exactly is that force and how much is that force? That's basically what we plan on learning today, all right? So let's go ahead and get started because it is quite a lesson here. These front pictures that I have here are just to help you realize that, in the clouds there are electrons, right? Before lightning strikes, there's tons of electrons. And then when lightning strikes itself, there's an electric force that is existing between the electrons and something in the water or something on the ground, which causes those electrons to be attracted and to come down to the earth, right? So let's go ahead and get started with the formula. This again goes into your blue formula sheet, and this is called Coulomb's law. All right. And Coulomb's law basically says that the closer two things are, the greater the force is going to be on them. This is very much similar to Newton's law, where he talked about a certain force that exists between two planets. And what's very cool about Coulomb's law is it kind of um, mirrors the law that Newton had. And Newton's law said G times mass of the first, mass of the second, over the distance between those two masses squared. And we used to use this for planets, right? We used to use this for planets. And it told us how much gravitational force existed between those two planets. Well, if you think about it, a proton and an electron, or a positive charge and a negative charge, they are somewhat like their own planets. And so what you'll find in this here lesson is it's really mirrored very similar to that. So you'll have a constant, which is k sub c, which we are going to use as 8.99 times 10 to the power of 9, generally speaking. And then we're going to use the charges of each one of those. So Q1 and Q2, they represent the charges of two different particles. And R represents the distance that is between those two particles. And when you calculate that, you're going to get something called F sub E, or the electric force. So you're calculating for the electric force, which we discover is also a field force, just like the gravitational force is a field force. If you forgot what a field force is, it basically means that two things don't need to be touching for them to have a force to be between them. Each of the charges, they are measured in a unit called coulombs, all right? And we talked about that in the last lesson. And here's something that I had asked you to go check up on. What exactly is coulomb spelled like? So there you go. That's the correct spelling. All right. I'm sorry, my spelling has never been that great, but there you go. That's the correct spelling of coulomb right there. And so each of the charges is measured in coulombs. The distance is of course measured in meters. And because electric force is yet still a force, and even though it was named after Coulomb, this is measured in newtons. Okay, so all that said, it's still measured in newtons. So we're going to be discovering a lot more about this law as we move forward. One thing you do want to try though is while we're here, we did this earlier when it came to gravitational force, where we saved the constant of gravity. So you should probably save Coulomb's constant, right? K sub c is known as Coulomb's constant. And so 8.99 times 10 to the power of, so E9, right? Just go ahead and store that right away as your value of, Bismillah, as your value of K. I'm just looking for K here. And then it's going to go ahead and store that for you, and that's going to stick there from now on. Okay, let's go ahead and try an example right away. So I will read this example to you, but I have copied down this problem onto a separate canvas, which is a little bit more manageable to write on, inshallah. So you have an electron and a proton of a hydrogen atom, right? We all know that hydrogen has a proton and an electron, are separated on average by a distance of about 5.3 times 10 to the power negative 11 meters. It says find the magnitudes of the electric force and the gravitational force that exists that each particle exerts on the other. And what we'll be needing this formula as we move over to a separate canvas to talk about this, inshallah. All right. So let me just orient you with the things that we have, and then we'll go ahead and get started. So the first thing that they told us is the radius between them is 5.3 times 10 to the power negative 11 meters. So that's something that's been given. And then furthermore, 8.99 times 10 to the power 9, that is Coulomb's constant. We've stored that in our calculator. Then m sub e and m sub p, we talked about this in the previous lesson. This is the mass of an electron. 9.1 is the mass of the electron, and 1.6 is the mass of the proton, right? So recall that a proton is much heavier than an electron. The electron has a much smaller mass as opposed to a proton is concerned. And then on the right side, you have a charge of an electron. This also we talked about in the previous lesson, right? So the charge of an electron is basically negative 1.6, whereas the charge of a proton, so it says Q sub P, is simply the same thing in positive, right? And notice how they're both measured in coulombs. And finally, if you recall, the gravitational constant is 6.673 times 10 to the power negative 11. That's the other thing that we used to use, and you'll probably need to use it in one of the sets or the homeworks. And you most likely have this stored if you check real quick, or just store it right now. So I'll go ahead and store 6.673, sorry, e to the negative 11. I'll go ahead and I'll store that as my value of, Bismillah, as my value of G. So there's that all done. Okay? All right. Now let's clear this, and we're going to go ahead and get started. So the question says, can you just go ahead and find the electric force and then find the gravitational force between these two particles, right? So the electric force is the first one that we'll find. So if you recall just a moment ago that I asked you to put on your blue formula sheet, the equation for electric force is K sub C multiplied by the first charge multiplied by the second charge over the distance between the two charges squared, right? So that is the equation that we'll be working with. And most of this is just going in your calculator, and the objective is to just make sure that you're able to do that. So that makes this 8.99 times 10 to the power of 9. I'll leave the units out just to keep the clutter out, right? All the units are set, they're good. And then comes the electric charge of a proton. So let's say Q sub 1 is a proton and Q sub 2 is an electron. So the charge of a proton is positive 1.60 times 10 to the power negative 19 coulombs. And the charge on an electron is a negative 1.60 times 10 to the power negative 19 coulombs, like that, right? And then all of that is essentially divided by the distance between the proton and the electron squared. So that is 5.3 times 10 to the power negative 11, right, meters squared. So as intimidating as the formula looks, and the numbers look like very small, and then the constant looks really big, it all really is going into your calculator. And I just want to take a moment and make sure you're able to put this in your calculator just fine. because it gets really frustrating, right? If you have everything correct, but then you put it into the calculator all wrong. So it says K sub C, and we already have K sub C stored as our K value, so I'm going to use that. And then the charge of the proton is 1.6, right, with the positive on it, times 10 to the power negative 19. Recall, having a negative exponent doesn't make it a negative value, it just makes it a very small value. So the 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 exponent on it is negative 19, like that. And then I have an electron, which is negative 1.6, right? And that is times 10 to the power also negative 19. So the only difference between a proton and electron is the difference of the positives and the negatives. And then you divide that by the radius, or the distance, we should say, between them squared. So 5.3 times 10 to the power of negative 11. We're going to go ahead and put those in parentheses, and then you're going to square that, right? So all that basically goes in your calculator, and you end up with an answer for the electric force, and the answer for the electric force is negative 8.193, negative 8.193 times 10 to the power of negative 8, right? Times 10 to the power of negative 8 newtons. And there you have it. That is the force that one proton and one electron feel between one another. Okay, then what we'll do is on the side here, we'll calculate the gravitational force. All right, the gravitational force is more a review for you. The gravitational force takes the mass of the proton and the mass of the electron, and it again uses the distance between them, and it squares it. So that is going to be 6.673 times 10 to the power of negative 11 multiplied by the mass of the proton, and the mass of the proton is 1.673 times 10 to the power negative 27. So 1.673 times 10 to the power negative 27. The mass of the electron is 9.109 times 10 to the power negative 31. 9.109 times 10 to the power negative 31. And then finally, the distance between them is actually the same exact distance as was used in the previous formula. So it's still 5.3 times 10 to the power negative 11 squared. So look at how similar those formulas are. But remember, one of them is telling you how much gravity they feel between one another, and the other one is telling you how much electric force they feel between one another. Both of them measured in newtons, though, right? Gravitational force and electric force. So here is, just really quickly to make sure that everybody knows how to do this, my gravitational constant was stored under G. I'm going to multiply that to 1.673, and that's times 10 to the power of negative 27, and that is multiplied by 9.109, and that is times 10 to the power of negative 31. So put that in right there. And then all of that is divided by 5.3 times 10 to the power of negative 11, and that is squared, so like this. And here is the answer that we get. We end up with positive 3.620 times 10 to the power negative 47. So 3.620 times 10 to the power negative 47 newtons, right? And that is the gravitational force, right? So before we move on to back to that lesson, just kind of give it some thought. What's stronger here, right? What's stronger here? Is it the electric force that's actually stronger, or is it the gravitational force that's stronger, right? And clearly, something that's got a power of negative 8 is much bigger than something that has a power of negative 47, right? And so what I'm trying to say here is and this is very important, when particles are very small, unlike planets, when particles are very small, when two units are very small, what really starts to matter is the electric force between them, right? And what's relatively negligible is the gravitational force between them, all right? So whenever you are talking about those two forces and it comes to protons and electrons, definitely the electric force is much more relevant than the gravitational forces. But we just want to show you that they both are relevant and they both do exist in this example here. Okay, so that's the first one that I wanted to try with you. And for this, you may pause the video and grab these answers from this slide over here. And what you want to do is, this is going to be as your homework, and this is part of the reasons why this is split up into part 2 lessons, is you're going to complete this exercise here, and then you're going to need to kind of upload your answers and stuff like that, like usual. And then, I'll list out the solutions, and then we'll go to part 2 of that lesson. All right? Now, the next thing that we're going to try is we're going to take a look at another example, all right? And this example is called the superposition principle. And after the superposition principle, basically you have yet another practice set. And it only has 2 questions to it. But, these are very telling. They're very important. And in the past, we've taken the entire class to kind of go over these as well. All right. So that's basically what we're going to be doing today, is we're going to look at what's called the superposition principle. All right. Now, once again, I've already listed this on my other slide, so I just want to orient you with what you're looking at here. It says, okay, now let's suppose that you had 3 point charges. All right. So if you don't understand what do they mean by point charge, we've got a little diagram for you here. So let's start from the bottom left here. So that right there is charge number 1, which is positive. This right here is charge number 2, and that's charge number 3. All right. Now, don't worry about the arrows right now. Okay, don't worry about the arrows. I will come to speaking to you about all of this. I think this example itself takes a while to go through. But here's a few things I will tell you, though, is we do know the charges of each one of them, right? The first one is a positive 6 times 10 to the power negative 9 coulombs, and then the next one is negative 2, and the next one is positive 5. And so the positives have been labeled as in red, and the bismillah, the negatives have been labeled in blue. And basically what we're going to be doing here is we're going to be finding the magnitude and direction of the resultant force, meaning what does Q3 feel, right? What does Q3 feel? So this is all about Q3, right? What is the feeling that Q3 gets from the other 2 charges that are present in the system over here? And as we're going through this, this is known as the superposition principle. Okay, it's known as the superposition principle. All right, so let's go ahead and try this question. Everything has been kind of prepared just to save as much time as possible. So the first thing that you basically want to do here is you want to begin by finding out the force that each one of these would be exerting on the third charge, right, or Q sub 3. So notice how there's 2 other charges there. So we're going to go one at a time, and we're going to look at the 2 charges and how they're exerting a charge on charge 3 here, right? So let's go ahead and begin with this, inshallah. So step number 1 is we're just going to go ahead and find each one of the charges. So the first thing that I write down is the force that is exerted on charge 3 by charge 1. See how I said that and then I wrote it, right? I wrote F sub 3 comma 1. So the force that's exerted on charge 3 by charge 1 is equal to, and of course we're talking about the electric force here. We're not talking about gravitational forces anymore, right? So this is going to be the constant, or Coulomb's constant, K sub C. And then it is going to be multiplied by it's going to be multiplied by Q sub 1 and then Q sub 3. All right, so Q sub 1 and then Q sub 3. And then it's going to be divided by the distance between 1 and 3, which is clearly labeled for us. It's told to us that the distance between those two charges is 5 meters. So we'll go ahead and we'll write in that this is over 5 squared. Okay, now you can pause the video and you can go ahead and calculate this by yourself if you wish. I will go ahead and demonstrate that even then. So here goes. I have a blank canvas here, and I'm going to begin by saying, okay, I need my Coulomb's constant. So my Coulomb's constant is once again stored under K. Then I'm going to take charge 1, and it's told to us that charge 1 is 6 times 10 to the power negative 19 coulombs. So 6 times 10 times 10 to the power of negative 9, I apologize, coulombs, so 6e negative 9. And then charge 3 is positive 5, right? E negative 9 like this. Okay, so we got both of our charges right there. And then you divide by the distance between them squared, and the distance between them was clearly labeled as 5, right? So you basically are going to divide by 5 squared, and the answer that we end up with is 1.0788 times 10 to the power negative 8. So 1.0788 times 10 to the power negative 8 newtons. And so this is the charge that is exerted on 3 by 1. Now, a question that I've gotten in the past is why are you talking about 3 and 1? It's because the question asked about 3. It says, talk to us about all the charges that are being exerted on 3. Okay, now what we're going to do is there's still more charges to be talked about, and the next charge that we want to talk about is 2. So you're going to run through that same exact formula again, except this time we're going to talk about the charge that 2 is exerting on 3. And so we're going to put in Q2 and Q3 and ask yourself, what's the distance between Q2 and Q3? And the distance between them is 4 squared, right? So 4, and you're going to square that, and that once again is going to give you a value for Bismillah, the force that is felt between those two. So I can use much of my old input if you think about it, right? All I got to do is I got to update the Q sub 2 in place of Q sub 1. So what I'll do here is I'll be clever about it, and I'll basically replace the 6 that I have here, and I'll insert instead a negative 2 in its spot, right? So I'll just insert a negative 2 in the spot, and I'll get rid of this 6 over here. So that takes care of that issue. And this right here is Q sub 3, and the distance between them is not 5. The distance between them was clearly labeled. It was 4. So I'm going to go ahead and change that 5 to a 4, and that 4 is still squared. And then I hit enter, and I end up with a new force that I need to talk about as negative 5.618. So negative 5.61875. And that one has a power of times 10 to the power negative 9. Now, before we move forward, one thing that I want to just kind of discuss with you is the fact that, I mean, most people understand this just from the beginning, but I just want you to know this, is between charge 2 and charge 3, there should be a force that is attractive, right? They should have an attractive force because those are opposite charges, and we talked about that in the previous lesson. So what does it look like as far as the symbol is concerned? When we talked about the electric force between 3 and 2, you will always notice that the sign is going to be negative because either one of them is positive and the other is negative, or the first one is negative and the other one's positive. So either way, that blue highlighting is there to remind you that whenever you see that negative, that means that that is an attractive force. And on the other hand, if you don't see a negative, meaning you see a positive there, then that means between 1 and 3, that is going to be a repulsive force, right? So they're repelling one another, sorry. And so every time that net force ends up being positive, you know that that's a repulsive force, inshallah. Okay. Now that we have done that, we're going to move on to step number 2. All right. And in step number 2, basically what we do here is now we talk about the component of the force that's exerted on 3 by 1. We talk about its x component. All right. We talk about its x component. And then we're going to talk about its y component. But usually the question you get here from students is, wait, why are we looking at x and y components of a certain force? And for that, now we'll talk about the arrows. Okay, so we'll talk about the arrows here. So let's focus on these arrows and let's kind of erase everything else that we've jotted down here just to kind of clear out that clutter. So if truly there is an attractive force between 2 and 3, right? What's really going to happen is, as far as Q3 is concerned, Q3, you want to observe this arrow. Let me highlight over it in red. So this Q3, it's going to want to go towards Q2, right? That's what attraction is called. So the force that's pulling it towards 2, which we labeled F sub 3 comma 2, we even calculated it, which is right over here, and I even said that it's going to be attractive. That's how much it's going to be. That's how much it's going to be. And we see that it's going to be pointing towards the force that is the negative force, or Q sub 2. Now, please realize the negative sign doesn't necessarily mean that it's pointing towards the left. What it means is it's really an attractive force, okay? So that's between 2 and 3, all right? Now let's focus on the force between 1 and 3. Right, now we did say, and we calculated this first, in fact, it's right up here. We said that that's a repulsive force. So what's really going to happen, if you guys focus on this line of sight, okay, if you focus on this line of sight, what's really happening is the third charge wants to get away as far as possible from the first charge. And so the quickest route for it to get away, the most direct route for it to get away, is it's going to want to go in that particular direction. So what we're seeing here is, in fact, there are two forces that are working on that are being exerted on this third charge, right? So if you were to draw, right, if you were to draw a free body diagram for that positive charge, right? Let's suppose that you wanted to draw a free body diagram for it. Well, here is what you would notice is, in that free body diagram, you essentially have two arrows, okay? You basically have two arrows that you're looking at, and one of these arrows is going to be pointing towards the left, and another one is going to be pointing upwards, right? So I'm trying to just find a good spot to put this in. I think this is for now it's sufficient, and this is what you want to really focus on. Okay, this is what you really want to focus on from that picture. We basically have two forces that are being felt. One of them is called F sub 3 comma 2, and one of them is called F sub 3 comma 1. Now you'll notice that 3 comma 2 only has an x component, but 3 comma 1 is our problem. 3 comma 1 not only has an x component, it also has a y component. So let me just remove this for now, right? Let me just remove that. And what I mean by this is, F sub 3 comma 1, it feels a force that is towards the right. So I'll call that F31x, and then it feels a force that is upwards, and I'll call that one F3 comma 1y, right? So now the question starts to balloon a little bit more. Now, you don't need to sit there and think about what the angle between them is. It was given to us that theta is equal to 37 degrees. So what we've essentially got here is, we know the angle between that is 37 degrees. So we have to go back to what we have done in the past in these situations, and we basically are going to do the following. to find that x component of the force, what we'll do is we'll take the F sub 3 comma 1, which we just calculated a moment ago. I'll just pinpoint for you where it is. It's right here in number 1. We calculated F sub 3 comma 1. But what we'll do more than that now with it is we're going to multiply it by the cosine of 37 degrees. And if you're wondering, why are you using the cosine of 37 degrees? I'll write this and then I'll erase it, or I'll try to leave it as long as possible here. But remember, the cosine of 37 degrees in this situation would be adjacent over hypotenuse, and adjacent over hypotenuse would be f31x over the hypotenuse, which is f31. And in that case, if you want to solve for f31x, you simply need to multiply f31 times the cosine of 37 degrees. And while we're here and we're talking about this, we might as well discuss f31y, right? So just, that's the subject matter there. But if you were to find the sine of 37 degrees, right? If you were to find the sine of 37 degrees, that would be what? That would be the opposite side, opposite over the hypotenuse. And in that case, that would be f31y divided by f3 comma 1. And now if you want to solve for f31y, which is what we're interested in now, you would need to take f31 and multiply to the sine of 37 degrees, right? So this is something that we've done before, but I just wanted to highlight that for you so you don't feel like I'm just dictating things to you, but you don't quite understand where they're coming from, right? So f3 comma 1, and this is multiplied by the sine of 37 degrees. Now just to be clear, we'll put these in parentheses, right? Because the notation f31 just looks kind of odd, but it's basically saying that take what you already had from before, which is 1.0788 times 10 to the power negative 8, and then put that into the appropriate spots, which we have aligned right over here, right? So that's step number 2. Basically, our job is to find the x and the y components of the diagonal force, and the x and the y components, we're going to go ahead and write them in to the step over here. So f31 x, we're simply going to go to our calculator and we're just going to punch into our calculator what we really need, and then we'll write it on this canvas here. So in fact, the thought process is what takes a while. The punching in the numbers is, it's something that we're quite accustomed to, right? So if you go ahead and you take a look at f31, it's 1.0788 times 10 to the power negative 8. So I'm just going to go ahead and write on 1.0788 times 10 to the power negative 8. All right, that's f31. And then we're going to multiply that to the cosine of 37 degrees. Let's just make sure our mode is in degrees, right? And then we're going to multiply that, to the cosine of 37 degrees. And when we multiply to the cosine of 37 degrees, we end up with 8.615 times 10 to the power negative 9. All right, so I'm going to go over here and I'm going to write in 8.615 times 10 to the power negative 9 newtons. Okay, and then we're going to do the same thing, but this time for the sine, and that's going to give us the y that we're looking for. So here is the sine, and that gives us 6.492 times 10 to the power negative 9. So 6.492 times 10 to the power negative 9 newtons. And so we've gotten the x and the y components of f31. Now, we talked about this earlier, but if you want to just be kind of complete about it, let's talk about f32, right? Let's talk about f32. Well, f32 has an x component, and f32, you can think of it as a y component. However, look at where F32 is pointing, right? Look at where it's pointing. It's only pointing in the x direction. So what I mean to say by that is all of the force that F32 that the second charge was exerting on the third charge, it's all an x component force, right? So I'm going to write in negative 5.1, negative 5.61875 times 10 to the power negative 9 newtons. That is the force that is exerted on charge 3, right? It's exerted on charge 3 by charge 2. And finally, just ask yourself, why is this 0 newtons, right? Why is the y component of the force that is exerted on charge 3 by charge 2 equal to 0? And the answer that you should get back is because it's not causing charge 3 to go up or down. It's just trying to force charge 3 to go sideways, right? So there you go. Now that we have those forces all written out, we're essentially done with step number 2. All right, so step number 1, let's just recap. Our job was to find those net forces. Common question I get is, why didn't you find F12? Like, what's the deal? Why didn't you do that one? It's because the question was never asking us for the force that's felt between 1 and 2. It's really interested in what's felt by 3. So we looked at 3 and 1, and we looked at 3 and 2. And then the next step that we did is we basically broke down any diagonal forces, as we've done before, into their x and their y components, right? So that's step number 2. Now, step number 3 is going to involve us totaling up the x components and the y components. So at this stage, this should somewhat ring a bell for you, like, oh my God, I have done something like this before. So we basically make 2 of these and we say, look, let's calculate the net force in the x's. And the net force, we can call it F net x if you don't like the summation symbol, is going to be F31x, right? The force that is exerted on charge 3 by charge 1 in the x's. And then we'll add to it the force that is exerted by charge 3 on charge 3 by charge 2 in the x's, and that right there will give us the net force in the x's, right? And we'll put that in just a moment. Then we'll think about the net forces in the y's. So the net force in the y is the same exact thing. We'll look at f3 comma 1 y, and then we'll look at f3 comma 2 y. Right? I realize that f3 comma 2y is 0, but this is just for having one set way of going about it so you don't mess up anything, right? So we already have the values for each one of these written in step number 2. So what we'll do here is we'll go ahead and just kind of calculate these values while we're looking at them. So for f net in the x's, we need to take f31x, which is written right up here. So 8.615, and then that's times 10 to the power of, bismillah, of negative 9. And we're basically taking this force and we're adding it to F32x, which is a negative force. So you can either add it or you can put a negative in front of it. So add negative 5.61875, and that's times 10 to the power of negative 9 like this. So when we calculate this, this gives us the net force that is felt by charge 3 overall in the x's, like which way is it being pushed. And so it turns out in the end, it really wants to still get away, even though it's being attracted, because that's a positive right there. So we end up with 2.996 times 10 to the power, 2.996 times 10 to the power negative 9 is the net force in the x's. The net force in the y's, we don't need to pick up a calculator, because if you think about it, the F3 2y, right, the force that is felt by 3 because of 2, that is actually 0 newtons. So really what's left over is the answer, and the answer is written right up here in that second row. So we've got 6.492 times 10 to the power negative 9 newtons. So although this problem, I understand it's a difficult problem and it's a long problem, but isn't this something that you've done before, right? Isn't breaking down components something also that you have actually gone through before? Right now, basically what you do in that final step is you're going to find the net force, okay, that is felt by that charge 3, and you're also going to find the angle that it's headed towards, okay? So for the net force, recall that this is essentially the Pythagorean theorem, and the Pythagorean theorem says take the net in the x's, right, and square it, and then take the net in the y's and square that, and that is your net force as far as that charge is concerned. All right, and we'll draw a final vector on it just to see which way it's headed. And finally, to find the angle, right, you probably have these written down from chapter 4 when we spent a lot of time back in November and stuff like that doing this. This is F net y over F net x. And yes, it's always going to be that way. Okay, so let's just go ahead and take a moment now that we've come to the end of this problem and calculate those net forces and the direction of the net force. So the first one is going to be the square root, okay, so the square root of 2.996, so 2.996 e to the power of negative 9, and what we want to do is we want to square this entire amount, right? So you can put a parenthesis around that, and then you can tell the calculator to square that, right? And then we wanted to add to 6.492, right? So 6.492, and that is also to the power times 10 to the power of negative 9, inshallah. And that is also squared. So when you put all that in, you end up with 7.15 times 10 to the power negative 9. All right, so 7.15 times 10 to the power negative 9 newtons. And that is the net force that is felt by the charge. Now, which way does the charge want to head, right? You have some idea because there's one thing that's pulling it towards the right. There's one thing that is pulling it upwards. We find out that in the net, the one that's pulling on the x's is still a little bit larger, and we realize that the y's are still existing. And so in the end, the direction that it's really going to want to go is that direction in the red, right? But to get that angle, is important. So let's go ahead and use the tan inverse ratio using those same exact two values that we just essentially had. So I realize this takes a little bit more time for me to type this all in, but I just wanted to make sure that you're comfortable with it and you're convinced by it. So F net y, once again, is 6.492. All right, so 6.492, and that's times 10 to the power of negative 9. And then we are dividing that, bismillah, by 2.996, right? So 2.9, I was just making sure I got the order correct because I've messed that up in the past, I know. Divided by times 10 to the power negative 9 as well. And then we do this, and we end up with 65.23 degrees, right? So we'll call it 65.23 degrees. And doesn't that look like it's about a 65-degree angle in the end, which way that it wants to actually head? Okay, so altogether, this problem, it takes about 20 minutes for us to complete. And basically, I'll just remind you of the steps. They're very straightforward if you really think about it. First thing that you do is you find those forces that are working on the charge that you're interested in. Let me zoom in a little bit. And then the next thing that you do is you break them down. That was step number 2. You break them down into their components. And after you break, I would say this was the trickiest part always for your class. So break them down to their components. After this, find out the net in the x's and the net in the y's. And finally, use the Pythagorean theorem to find that net force on that particular charge that you're interested in, and then find the angle that that would actually be headed in. All right. So for this, you're going to have practice set B. So if you would like to take a moment and you would like to copy down these answers right over here, that way you'll know what to work towards, right? So I'm already giving you the answers, no hiding there, inshallah. And this is practice set B. Basically, this is the other thing that is due. So we're about halfway through the lesson, inshallah. And I will, inshallah, stop here. And so good luck in doing the homework. You're always welcome to ask me questions, and I'll do my best to inshallah answer them. Thank you, and Assalamu alaikum.